Did it?
Hello,
Um,
2023.
so how is your weather there, Morgan?
Well,
You're
1 week ago
Nashville, right?
today, it was 0 degrees Fahrenheit, so
Oh,
whatever that is in magic units. And today it was 70 degrees, which is like, almost summertime.
so you
So
went
we
from
have,
zero to you really had a 70-degree difference in the matter of
yeah, so
days.
that's what, probably like, 25 degrees, 25, yeah, huge swing.
Wow.
Um, and yeah, so it was like we were, pipes were freezing this time last week, and today, um, it's like I could almost wear shorts.
Are they equipped for freezing pipes there the way they weren't in Texas?
We are definitely better than Texas, but I mean, when we had the record low, when we had the temperatures at zero, they were all-time records.
Yeah.
And so there was definitely infrastructure damage that happened, but not like they did rolling blackouts here and there because the power grid, we have a lot of heat from electricity here, and so that was a rough time.
Yeah.
But
Yeah.
not in Texas where it was like the world fell out.
Yeah, we hit minus 14 here on the mountain, and I'm about 2 degrees Celsius colder than down in the city. So they had about minus 12 down in the city. But that so that you were colder than we were. And
It
we
was
went through a brutal cold snap here in Western Canada, and
it
still
was
you were worse than
shocking.
us.
It was shocking how
Yeah.
cold it was outside, and it dropped. It literally dropped 25 degrees Celsius in 4 hours.
Wow.
It was like when I left for work, it was spring temperature, and when I got home from work, it was like Antarctic. It was just amazing how fast it came on.
Oh, that's incredible.
It was
Huh.
from a weather perspective, it was really cool. From an everything else perspective, it was just
Yeah.
like,
But you
oh,
got hit by two, right, Pamela? Hmm. Wow. Oh, all right. You're we hear you. Well, how about you, Eddie? Where are you?
I'm in Southern California,
Yeah, so you're about to
and
get hit by this bomb cyclone.
absolutely, it's been unseasonably rainy, which is a very good thing for us.
Yeah.
We need to refill those
Yeah, you need
reservoirs.
it. Yeah. Yeah, we had again like a super weird year. We had the wettest spring, we had the driest fall. This winter's kind of normal, but it's apparently like the third year for La Nina, I think, at this point, and now it's supposed to shift over. So next year could get weirder, right? Or hot.
yeah, they've been saying it's going to be a weird winter this year, and I guess we're seeing a little bit of that so far.
Yeah, yeah. All right, let's get started. Everybody ready? Okay.
Yeah,
I thought I heard Pamela
there was a moment.
breathe in anticipation. All right. Hello and welcome to the Weekly Space Hangout for Wednesday, January 4th. Say it with me, 2023. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about cool dark nebulae, how to get the cosmonauts home, more evidence for modified gravity as dark matter, and a giant eruption on Io. Joining me this week, we've got our engineer behind the scenes, Dr. Pamela Gay, on the camera. Pamela.
These things happen. I'm always happy to step in, and yeah, it's a slow but interesting news week.
Yeah, it definitely is slow. I can feel news starting to percolate out again, but it's been definitely quiet here behind the scenes at Universe Today Productions. So, but I think the quiet time is about to end. And we've got Dr. Morgan Renberg. Hey, Morgan.
Hey everyone, Happy New Year, 2023.
Yeah,
It's going to be hard to top last year in terms
yeah,
of space news, but I
yeah,
think we
yeah.
can do better. We can do better in the rest of the world.
we, yeah, exactly. All the other stuff should come online with how good space can be. We've had this vision of like a perfect year in space. Let's have that like in climate and in international peace relations and in all of that health. All right, come on, science, catch up with space. All right. Now, before we get into this week's special guest, I want to give a huge shout out to our good friends and fans of the Weekly Space Hangout crew. You can join this amazing community, talk with other space fans, especially during the long, dark hiatus over the summer. So go to wshcrew.space and you can join this amazing community. All right, let's get into this week's special guest. We've got Dr. Eddie Schwieterman. Is that right? Did I say it wrong again? Schwieterman. Yeah, I did it wrong. I practiced before. I still got it wrong. Schwieterman. Okay. Thank you. Welcome to the show.
Thank you very much for having me.
All right. The question I always ask people, who are you? What do you do?
I'm an assistant professor of astrobiology in the Department of Earth and Planetary Sciences at the University of California, Riverside. My research lies at the intersection of planetary science, exoplanets, and astrobiology. I think about the evolution of planetary atmospheres, specifically rocky exoplanet atmospheres, relating those to the evolution of Earth's atmosphere and the interaction with the evolution of life on Earth. And so one of the things I think about a lot is how we could potentially find life on other planets.
And you came up to our attention with a paper that you published, I think, in the journal Astrobiology, about nitrous oxide as a potential biosignature. So can you talk about this?
Yeah, we recently published a paper in the Astrophysical Journal that evaluated the potential for nitrous oxide, which is laughing gas. You might be familiar with it if you've been to the dentist recently. But it's a product of microbial metabolism on Earth. There's about 330 parts per billion in our atmosphere, and it's one of the indicators in our atmosphere that life is present. But we think that the amount in our atmosphere could have changed drastically through geologic time as the chemistry in our oceans and atmosphere altered through time, and that other planets may have potentially more nitrous oxide than Earth. And this could be a very compelling indicator of life on exoplanets, given the right context.
And like with biosignatures, what is like the hallmark? What would be like, what's a good biosignature that you're looking for in general?
Yeah, so a biosignature is something that's produced by life that can survive and build up an exoplanetary atmosphere, that produces observable spectral signatures that we could find with a telescope in space or on the ground, and that can be separable from abiotic processes. So it's so here's a great graphic. This is from the journal Astrobiology, from a set of review papers, and Aaron Gronstel, I believe, was the artist that produced it. And this really illustrates just how interdisciplinary this field is. We got to know not just what life produces and what we could find that is a product of life, but what life may uniquely produce, or the combination of things that life might uniquely produce. So one of the canonical examples is the oxygen in our atmosphere, which is primarily, almost entirely, from photosynthetic life on Earth. And it exists in a disequilibrium with the methane, which is also generated by biology. Well, the trick, of course, is that those two things can have some minor abiotic contribution on Earth, and on other planets, those could be bigger. And so what we need to do is be able to differentiate the molecules that can be produced by life and the same molecules that may be produced by abiotic processes. So what combination of those molecules is actually a compelling biosignature? I mean, and how could we find it?
I mean, I think about the search for life on Mars, for example. And the big problem with a lot of the searches so far is that they've been inconclusive. And methane has been detected on Mars. And I think for the longest time, methane was thought, well, this is your perfect signature. It has to be generated by some process, probably life. Why is like methane, carbon dioxide, like why are these, I mean, ozone, like why are a lot of the things that we think of as the byproducts of life actually not great biosignatures?
Well, it's all context dependent, so I wouldn't go out of my way to tell people who are saying let's look for methane, let's look for oxygen, that those are bad biosignatures.
Don't do it.
There's certain complications, and so there's a slide I have, that shows the planets of the solar system. Methane is not uncommon on planets. So it is made in equilibrium in the gas giant planets. We see it on Titan. We don't think that there is. So this is a great illustration of our own solar system. The way that methane is made on these planets is very different than the way that methane is made on Earth. Right. But it's still there. And so it kind of proves the point that you need to have context-dependent analysis. Venus and Mars have CO2-dominated atmospheres, but because of the photolysis, the breaking apart of the CO2 by ultraviolet photons, you do get a teeny bit of oxygen and ozone. Not nearly as much as on Earth, just a very small amount, but it's observable. The combination of lots of oxygen and lots of methane is only seen on Earth. Moreover, significant portions of abundances of nitrous oxide only seen on Earth. And so Earth is or nitrous oxide is sort of unique in this diagram here, where Earth is the only planet with it, and Earth is the only planet with life.
Like at all? Like nitrous oxide has not been found on any of the other worlds in the solar system?
Well, it's always a matter of equilibrium product. And what that means is that it's not made, you take a gas mixture and you just give it a certain temperature. Nitrous oxide really isn't a common thing. It is made in very small quantities through reactions with ice, like nitrogen ice surfaces in the outer solar system and cosmic rays. You can make a teeny bit of nitrous oxide that way. But yes, in terms of free nitrous oxide in the atmosphere, Earth is pretty unique in the sense that we have that nitrous oxide and the other planets don't.
And so like part of like the problem, like if you could just directly sample the atmosphere of some other world, you could measure the parts per million, parts per billion of each one of these gases and probably know conclusively, right? But the problem is that you're using spectroscopic data. You're looking at these chemical signatures of these planets. Is there no way to get ratios through measuring the chemical signatures?
Yes, so you can look at the spectra of the planet. The spectrum of the planet, you take the light and then you split it up into its component wavelengths. And each molecule has a unique signature that it imprints on the spectrum of the planet. The strength of that signature is dependent on the abundance of the gas. When we're talking about real observations, of course, if we look at Earth, we find that we have all these things in the atmosphere. You have infinite resolution. As you said, you could directly sample it. You could see oxygen, methane, ozone, nitrous oxide. That would be a very, very compelling set of molecules to find together that would tell you that there's life. But you need a certain amount to create a spectral signature that's significant enough. And you don't necessarily get the exact abundance because you have to think about the noise. Mm-hmm. And the fact that when we're talking about looking at a planet that's being outshone by its star by a factor of 10 billion, which is true for the Earth and the Sun, we're not going to get perfect data.
And you're seeing what's at the cloud tops, which may not necessarily be what's deeper below.
Certainly, the clouds have a big impact on the detectability of gases in atmospheres. It depends on whether you're looking at the planet as it's transiting the star. That clouds are really, really impactful then. If you're directly looking at imaging the planet, and the planet is like Earth, there are some paths that are free of clouds, and you can see all the way to the surface. Of course, you're mixing up the clouds and the surface when you're looking at an exoplanet because everything is convolved into a single a smear of pixels. So you're really looking at the average of the whole planet, which includes clouds and no clouds.
So, I mean, nitrous oxide is an interesting candidate, but does it more seem like is it really about multiple molecules working in concert in an atmosphere to give you a more solid understanding of whether or not there's life generating these chemicals?
Absolutely.
Yeah.
We'd love to see nitrous oxide. So our point is that nitrous oxide, if we found it, would be a compelling signature, but it's not enough by itself. Right. What you want to do, because there's some small quantities made by lightning, if the star was very active, we've gone through different scenarios in which you could make nitrous oxide abiotically. If you had a very intense stellar activity, you could break the together the nitrogen molecule that's N2, very tightly bound. Usually you can't break it apart. And that's actually why one of the reasons why nitrous oxide is a compelling biosignature is because life can break it apart and create a cycle that eventually results in nitrous oxide. It's hard to do otherwise. But if you had a lot of stellar activity, you could also potentially generate nitrous oxide that way. But what you would do is then you'd look for, is the nitrous oxide present with oxygen and methane, or is the nitrous oxide present with other molecules that you'd expect from that robust stellar activity, which might tell you, no, this nitrous oxide is actually being made by an abiotic process.
And So in searching for these kinds of chemicals, where is the balance? Like, people said we should just look for fluorocarbons because you don't get those naturally in nature. It must be evidence of some technological civilization. Do you think would be like the perfect molecule? I mean, I'm assuming if there was the perfect molecule, you would have already thought of it and would have already written a paper on it. But what kind of characteristics would the perfect molecule have in your mind?
Yeah, so one of the characteristics, of course, is the specificity of the molecule, right? How specific is it to biology, or in the case of CFCs, that's technology. You actually do get some fluorine molecules from volcanism, very small abundances. So it kind of just proves the point that you always have to think about the context. Probably you could never get as much as we're generating through industry, but sort of biosignatures are the same way. How do you get that much?
Sorry. So it could be a natural way to get chlorofluorocarbons, volcanoes and chemicals mixing.
Yeah, for example, sulfur hexafluoride is a insulator that's really mostly entirely made by industry on Earth, but there is a very tiny volcanic source of it. And so if you're thinking about, if you want to play devil's advocate and you're thinking about what if the chemistry was just really weird on this exoplanet, you can play those games. So like you said, it's a matter of the context of the combination of molecules that you can see that's telling you. So for example, what we did was we said, given this amount of the gas, nitrous oxide, how much would have to be produced by the surface given its destruction rate from the star? Because photons can break apart nitrous oxide. And really, if you find a certain concentration of it, that implies that there's a production rate of it. And that production rate on Earth is huge. Okay, so it's much bigger than you could get from an abiotic process. And so you'd use the same kind of logic for other molecules. Is really the biosignature is the flux. Do you need a gigantic photosynthetic atmosphere in order to generate the amount of production in order to give you that spectral signature that implies this abundance of the gas?
So if you looked at Earth from different distances, like say you were able to block out the light from the sun, you had that coronagraph that was getting rid of the pesky sun, and you were able to just resolve the light of the Earth. And say we had like JWST or some even more powerful telescope, what kind of distance range would be, like, obviously if you were looking at it from Mars, you would go, Earth is absolutely a planet covered with life. We could see the green, we could see the blue, we could see the clouds, like there's life there. How far away would Earth be certain to have life, and at what point would you be back to it being an ambiguous question, do you think?
Well, there's a trade-off between the distance, which is really important for the signal to noise, and also the size of your telescope. We did
big as you like. Well, I mean, solar gravitational lens telescope. I don't know, something.
Yeah.
20 meters.
Well, certainly, right. Certainly, if you had that solar gravitational telescope, you could look at the migration patterns of exobuffalo on the planet. And that would be a very strong biosignature. The point is that
volcanoes make exobuffalo.
Depends on your rule. But we did look at, could JWST do it, and JWST could potentially find nitrous oxide if the flux were significantly higher than Earth's, but well within what we think is reasonable for an Earth-like ocean, and we were looking at the TRAPPIST system. And so that's really our best chance for JWST finding something like nitrous oxide and finding something like methane on an Earth-like planet in transit observations. Right now, we don't have the capability of doing the reflected light or the emitted light, but there are ideas out there for space-based infrared telescopes, or these large 30-meter ground-based telescopes. They would be able to do more, and we're talking about planetary systems within about 30 light years.
Right, where you could feel pretty certain that you're looking at life on this other world.
Yes,
with the combination of the chemicals that you're sensing in its atmosphere. It's a funny thing, I think. As exoplanetary science grows, as new telescopes come online, as astronomers get better and better at what they do, I think the public is expecting there to be this moment where someone stands up at a podium and says, "We found life." But it's not going to be like that, is it? It's going to be like the phosphine discovery. Maybe there's something there, maybe not. People are going to write papers and say that it is. People are going to write papers and say that it isn't. How do you think that'll unfold?
Well, this is the beauty of science, is that you can't just say something is the way it is and people will believe you. There will always be scientists out there and other members of the public questioning it. And I think what we really have to do when we're talking about something so monumental and so important as finding life on another planet, that we just really have to tolerate ambiguity for a while. So we're going to get a strong hint. Let's say that there is a planet with life out there and we find a signature. That first announcement, as you said, it's not going to be we found life on a planet. It's going to be we found weird chemistry on a planet. It could be indicative of life. It could be indicative of something else we haven't thought of yet. And we're going to want to do more observations. And I would be very distrustful if someone said, disregarding the possibility of aliens landing in the White House lawn, I'd be really skeptical if someone said, this is, at the first observation, this is definitely life. It's going to play out. There's going to be a scientific process, and that's a good thing.
Yeah. I mean, you get the Viking experiment otherwise, where people are still fighting 50 years later. But whether or not...
ALH 84001.
Yeah. Right. Exactly. I do recall President Clinton standing up and saying we found life on Mars, and it not being necessarily true. So place your bets. When do you think we'll find life?
It's such a big question, and maybe I'll do the political thing and not answer the question, but answer a different one, which is that I think that it is a generational goal, a sort of a civilizational goal to find life.
Yeah.
And you can think of it sort of like gravitational waves, where we know that there should be gravitational waves, and it took 50 years, right, of development in order to get there. And I think that this is a goal that's worthy enough to wait. If we don't happen not to get lucky, JWST could, if there's habitable, inhabited, highly biologically productive planet in the TRAPPIST system, we could know in the next few years. But absent that, let's say maybe not super strong possibility, I'd say over under 20 years.
And how would you feel if we kept searching and searching and searching in an ever expanding sphere with more clarity and not find anything?
I think it's still meaningful because we're setting limits on the prevalence of life. And there's this Buckminster Fuller quote. It's like, sometimes I think we're alone and sometimes I think we're not. But either way, the fact is staggering, right?
Yeah.
We're, how much would we appreciate our own planet and our evolution on this planet if we knew it was 1 out of 1,000 or 1 out of 1,000,000 or 1 out of 1,000,000,000?
Yeah. Well, if people want to keep track of your work, what's the best place to do that?
So I have a website. It's actually eddyschwieterman.com. Redirects to it. I'm also on Twitter at @NoGreenStars.
No green stars. Right. Now I remember. Okay. Yeah. Well, Eddie, thank you so much for taking the time to chat with us today, and good luck with your search for life in the universe. If you do find aliens, please let us know.
Thank you very much, Fraser. Thanks for having me.
All right. Take care. All right. Let's move on to the space news portion. Pamela, let's start with the pretty picture.
Okay, let me pull up the pretty picture so we can better talk about it. I have this very large, curious question mark on that screen. One moment while I debug. So thank you for your patience, everybody. We are working on figuring out a whole lot.
Do you want me to go to Morgan while you engineer?
That's not going to help me figure out why there's a giant question mark.
Well, you won't also have to be thinking about how to explain your story.
My pictures are not important on
let's go, Morgan.
Story.
Observational evidence for modified gravity. Dark matter is not stuff, it's gravity.
Dark matter is dead? Exclamation point? This story comes from our good friend Brian Kerberline. And it caught my attention because you hear about all these like crackpot gravity ideas. Like, I don't know, your inbox is probably as full of them as mine
chock-a-block
is.
full with them, yeah.
And you never really think, hey, that could be true, and they're not usually. And I don't want to say that this is a crackpot idea, but to set the stage here, for the last 60 years, we've had this picture of the universe where we have a bunch of normal matter and then a whole bunch of extra matter that we can't see, that doesn't interact with light, but has gravitational effect. That's what we call dark matter. And the need for dark matter arises out of observations that galaxies basically wouldn't stick together under the force, the gravity of the stars and the mass that we can see alone. Basically, galaxies are spinning so quickly that they ought to be flinging their stars into the universe, and yet they are not. We don't see enough stuff, so we made up this thing called dark matter to explain what is there, but we can't see it.
Right.
We've now been looking for decades and decades for this stuff, and we haven't actually seen it. We've seen the effects of it in lots of places beyond galaxies. So that picture that Pamela's got up there, for example, shows a cluster of stars whose light are being, a cluster of galaxies, excuse me, whose light are being warped by the effects of what we think is dark matter, stuff that we can't see. So we know the effects of it are there, but we haven't found a suitable particle that actually carries it. And so we don't really know physically, like the gooey stuff, what is it? And as this theory has kind of stretched on and not borne an observational result, people have started to look for alternative explanations for what's going on.
But the alternative, sorry, Morgan, like the alternative was always known. Like right from the beginning, people said either there's a particle that we can't see, or we don't understand gravity. That gravity at the largest scales does something weird.
Right, yeah, that's fair.
Sure. You're muted again, Pamela. Pamela, are you muted?
Pamela's saying really smart things about gravity.
Well, that's it. I think Pamela gets the Nobel Prize. Moving on.
Yeah.
Okay, sorry. I fixed my audio and then I forgot to put that live. All right. So what I was saying is I have to stop you at the idea that gravity is not understood. It's that it's not fully understood. There was Newtonian gravity, which is perfectly fine for throwing baseballs. There is relativistic gravity from Einstein, which is great for GPS. And so the remaining question is, do we need a additional term, an additional understanding to get us to understand the most distant applications of gravity?
Yeah. And so, but I think observationally, we saw so much evidence piling up that it is some kind of cold particle that clumps with gravity. So the I guess the additions to gravity had been fallen out of favor. Now
so let's talk about what this alternative is, and that's very well stated by Pamela. The idea here is basically, so the big category of this is called modified Newtonian gravity or modified Newtonian dynamics, which exactly reflects what Pamela is saying. Newtonian ideas of gravity, basically that you have this 1/r² relationship to gravity, works. We know it works across all of these things. However, there's parts of the universe basically where it hasn't been tested in the same way, that we don't know that that's all that there is. And the idea behind the sort of most common idea here is basically that in addition to your 1/r² regular gravity force, you have an additional bit of force that's kind of like always there. It doesn't really matter where you are, there's this extra little bit that's always there. So if you took your distance to infinity, in theory, gravity would go to zero, except in this it wouldn't. It would go to some very tiny, very, very, very tiny amount that is insignificant, immeasurable here on Earth. Even in the solar system, we can't measure that. But this tiny little tweak at galactic and intergalactic scales is enough to sort of tilt the scales of what we see happening mechanically in the universe to account for the observations.
Right.
The study that we're talking about today looked at 152 galaxies that had been previously observed by Spitzer. And it basically looked at the mass distributions in those galaxies. And under the sort of dark matter world, you would expect that you average all those together and you would basically see a smooth distribution of matter from the inside to the outside. However, when they actually did that, what they found was this little like kink in the distribution in which the difference between the matter on the inside and the outside, like the density, was not exactly the same. Or was not continuous, I should say. It wasn't smoothly varying. And that kink is not accounted for or predicted by dark matter, but it is predicted or accounted for by this Newtonian dynamics, modified dynamics idea. And that's just one bit of evidence. And as Fraser said, there's lots of reasons to think that dark matter is a good explanation, even if we haven't found the carrying particle for it. But this is maybe the first time in a while where there's been maybe a strike against dark matter in favor of an alternative explanation. And so that's just cool. I think that it stuck out to me because it seems like, for 15 years it's been, yes, dark matter this, dark matter that, but we just can't see the thing. And now suddenly we're saying, well, yeah, there's a lot of evidence for dark matter, but there's also evidence that suggests our understanding of that idea might not be fully complete either.
Yeah. And it's interesting, like the work that was done, it was a Korean researcher, just by doing this giant survey of all of these galaxies and being able to line up and have the evidence point in that direction. It's interesting though, when I talk to dark researchers, they're almost certain that dark matter is going to end up being a whole bunch of things. Like it probably will be particles that we can't see. It'll be particles that we didn't even know about before, but could be a little bit of us not understanding gravity at the larger scales as well. That all will come together bit by bit and add up in the same way that we had the regular missing matter in the universe, and people worked out that some of it is the gas clouds in between galaxies, and some of it is other material, etc., and piecing it all together.
There's rarely a silver bullet in nature.
Yeah. Where someone says, "We did it. Yeah, we made it."
So I have to know. I have to admit, I didn't know this story. Is the only non-behaving one they found the Sagittarius dwarf galaxy?
I think it was a statistical.
It
was a meta-analysis of all of these, the distributions of all these galaxies, and they're making a statistical argument basically that the distribution, the mass distribution function basically of these galaxies is better predicted by the results of modified Newtonian dynamics than it is by dark matter.
Okay.
This is not we looked at one thing and saw something. This says, we looked at a bunch of things and the odds are better that this is what you would see if the explanation was modified gravity than dark matter.
Yeah.
So this is circumstantial evidence, but we've had a lot of instances in the past where circumstantial evidence has lined up on the side of dark matter. Yeah. And this is an example where that isn't the case, but it's also only 152 galaxies.
Yeah, well, I gave you a link to the paper, Pamela. You can definitely check it out. I think you'll find it interesting.
I was foiled by the graphic on Universe Today, which is very pretty, but only labels the Sagittarius dwarf galaxy.
Right. Yeah. All right. Are you ready? Speaking of pretty pictures, have you got your picture?
I think I am. I think I am. So I have a story on a license plate of a galaxy. And of course, I have looked up other things. So I'm going to tell you, this is not a galaxy, of a nebula. This is a nebula in the Serpens, the Serpent constellation, which happens to have at the end of its tail 3 different little tiny star forming regions, and 2 of them had already been imaged, both in normal optical wavelengths that we can see with our eyes, as well as in the beyond red that we can see, infrared colors that JWST is sensitive to. In the extreme cases, but in this case, it's actually data coming from VISTA, which is the Visible and Infrared Survey Telescope for Astronomy, which is on the Very Large Telescope down in Chile. And their goal in using this system was, first of all, if you have the ability to image in 67 million pixels, you look at the most amazingly detailed stuff you can look at. And second of all, with the infrared wavelengths, they're able to cut through all of that dust and gas that blocks our visible light view and see all the different stars that are embedded inside the nebula, as well as a few that are behind it. And what's absolutely amazing looking at this pair of images, where the redder looking one, that's the hydrogen gas that we're seeing, the lower right one that looks so much clearer while we're looking through that red emitting dust. You can still see in both images, however, these bands of darkness, and those bands of darkness are actually areas where thick molecular gas and dust is still able to block the light of the stars behind it and any star forming proplyds that happen to be inside. This is your classic idea of a dark nebula. That's where the star forming will eventually make its way toward, but it's not there yet. This is just a beautiful system, rich in star formation in the center, migrating outwards to where there's still the dust visibly blocking light.
And this nebula, I've taken pictures of it in the past. It's in Serpens, which is very close to Sagittarius.
Yes.
It's the same constellation where you can find the Eagle Nebula.
And the Omega, which is
and the
another one
Omega
you like.
Nebula.
Yeah.
Yeah, absolutely. I love both of those star forming regions, and this one's great too. But I really like that infrared view where you see that dark nebulae. It's a lot more visible in the infrared, but it's such a great picture.
And this really gets across the idea that if you have some dust and gas, the light can still make it through. But as you get more and more, you eventually block the light. And we see a different version of this in our own sky with sunset, because the bluer colors of light are blocked more easily than the redder colors of light. So, or scattered, I should say. So sunlight coming through at noon, you have the blue light scattered in all directions, but all the other colors easily make it through. And not all the blue is scattered, otherwise we wouldn't see in blue. But as the sun gets further and further towards the horizon, it's going through more and more of that atmosphere. And so more and more colors are getting blocked. Well, in this case, in the first image, you see even the reds aren't able to make it through the clouds of gas and dust. But then when you go into the infrared, now the infrared image can mostly make it through, but even that can't make it through in all the different places.
All right, let's move on. Morgan, let's talk about Io's volcanism.
Yeah, so there's a cool paper that came out recently talking about an eruption on Io that happened second half of 2022. Just one of the oodles of cool things that happened in space last year. So you see a picture from one frame of this observation. And Io is, by far the most volcanically active location in the solar system. It's kind of like a tiny object with giant volcanoes. It's like a volcano in space, basically. And it
That's awesome.
And its output basically paints the entire Jovian system. So you can't really find a spot in the Jovian system where there aren't stuff from Io's volcanoes. And so they're highly interesting to us from the perspective of the evolution of the system, but also from the possibility of life. Because volcanic material is full of yummy organic stuff, and as it falls down onto the surface of Europa, it might be filtering into Europa's oceans and providing the chemical basis for life to sustain. Of course, we have Juno there right now, looking at the magnetic environment of Jupiter up close, but it's much easier to see the effects of something like this from Earth, where we can get the really wide-angle view. Now, this is really cool for kind of two reasons. One is the sort of science observation side, and the other is how they did it. So let's talk about how they did it first. This was detected by the Io Input-Output Observatory, which has the cute name Io. And it is basically a telescope that you could go to your neighborhood telescope store, pointed at Jupiter with some fancy equipment attached. And so if you were a particularly well-to-do amateur astronomer, or you were like a little liberal arts college observatory, you could buy all the stuff to do these observations and contribute to the real science. It's a telescope. It's got a coronagraph attached, which means basically that it has a little thing in the middle that blocks out the light from something really bright. In this case, we're talking about Jupiter. We often use them to look at stars or the sun. But here we're blocking out Jupiter. That's what's making that black line that you can see there in the middle. And then it's got a filter on it that is allowing it to detect sodium and sulfur. And these are elements that we associate with volcanism. They're also highly associated with Jupiter's torus, which is this structure of ionized plasma that is picked up by the magnetic fields of Jupiter and kind of swirled around the Jupiter system. And this is what's responsible for a lot of the deposition of Io's stuff onto the rest of the solar system, or onto the rest of the Jovian system. So the Io instrument takes pictures like this and looks for these big streaks like you can see there on the right, which is evidence of emission of sulfur and sodium that are above the sort of background levels for this system. And so it started seeing a big increase in July, and that increase existed from July all the way through December of 2022, so just last month. So you think that's a 6-month volcanic eruption that's filling the Jupiter system with ash and ionized material, etc. So that's kind of the cool observation side. Scientifically, what's cool is that the plasma torus actually did not absorb nearly as much of this material as it usually does. And that's kind of a mystery. It could be that what's being erupted here is different than usual. It could be that the way it's interacting with Jupiter's magnetic field is unusual. We don't really know because all we can see is the sodium and the sulfur, but there's going to be lots of other stuff that gets picked up or it gets erupted from the volcano that we just can't see.
So, if we could fly to Io, and I guess Juno will be doing this very soon, and we could see this volcano erupting, what do you think we would see?
Well, we've actually seen volcanic eruptions. Cassini New Horizons caught volcanic eruptions happening on Io as it flew past on its way to Pluto. And they look quite a bit like volcanic eruptions on Earth. They tend to be larger. They tend to be more diffuse because there's a lot less gravity on Io than there is on Earth. But they look, kind of like, the billows of smoke that you see coming off of a tire fire or something. But they're hundreds or even thousands of kilometers long.
Yeah.
And so they match our intuition, but our brains can't really make sense of the scale.
I think I'm remembering a picture where it looks almost like a water fountain.
Yeah,
that made this little dome of lava on the surface of Io.
And you can see the just plumes of gas and dust coming off of them. And And when New Horizons, and maybe even when Cassini, but definitely when New Horizons flew by, there were like 4 or 5 eruptions happening simultaneously at different scales on different parts of a moon that's smaller than Earth's moon, significantly smaller than Earth's moon.
Yeah.
And that's the level of volcanism we're talking about. We think Earth has a big volcanic eruption, once every few years. It lasts usually for like a few weeks. To have, major volcanoes happening, erupting for 6 months at a time it would be awe-inspiring if it wasn't just totally terrifying.
Yeah. It makes me sad that the mission to Io wasn't chosen on the last batch. We got 2 missions to Venus and no missions to Io and no missions to Neptune, Uranus.
Well, I got some good news for you, Fraser, which is in 1 year, at the end of 2023, in December, Juno will be making a close approach to Io. It's currently doing some complex orbital mechanics to kind of realign its plane, but in a year, we will be doing a close approach of Io, and that will be fascinating to understand from Jupiter's plasma science side how the magnetic field and these ejecta plumes are interacting on the small scale. But we're also going to get some amazing pictures from the Jupiter imager as
Will
it comes in.
Will it be closer than other spacecraft have flown? It's going to be just a couple of 100 kilometers away from Io, right?
I don't know the exact geometry
I don't know how close
of what
it's
this
gonna be.
observation is going to be. We did get we had some great photographs from Galileo, from Voyager, but yeah, nothing like we've seen from some of the other planets.
You can tell when a spacecraft is starting to wind down when they send it on these dangerous.
They go sightseeing.
Yeah, time to go into the danger zone, into the magnetosphere of Jupiter, and get punished by the radiation, but also take some pictures of some objects like Io that are really exciting.
Well, the Io, there's part of me that's like, it feels like flying over Iceland during an eruption where you think you're probably going to be above the ash, but you're just not quite sure.
Yeah.
This Taurus is kind of amazing.
Well, if you look at that picture, that eruption is like 20 RJ, Jupiter radii.
Yeah.
In size. This is no small feat to fly through.
Yeah.
Yeah.
Yeah. This is going to be exciting. All right, Pamela, how are we going to get those cosmonauts home?
This remains the open question. So for those of you who escaped the news cycle for the past several weeks, first of all, tell me your secrets. Second of all, back on December 15th, it was noticed that there were a bunch of weird flakes coming off of the MS-22 Soyuz capsule. And as everyone watched on NASA TV Live, in growing horror, it was realized that something was leaking from the capsule, and they had no way to stop it. What was leaking was identified as the coolant, which is generally something you want your spacecraft to have. And since they didn't have a way of stopping the leak, it continued for the next many hours until the spacecraft was emptied of this particular coolant. Now, in the days since then, which has turned into weeks since then, they have done what they could first with the robotic arm that the Russian capsule has, and then with the Canadian arm to try and take high resolution images of what's going on. And they were able to figure out there is a hole that appears to be 0.8 millimeters in size. It's unclear if it was caused by the space debris that is becoming more and more ubiquitous. or if it was caused by some sort of a micrometeorite. Initially, there were some folks speaking out of turn saying it may have been a geminid, but the angle that it would have had to have come from is inconsistent with it being part of the meteor shower. Whatever caused this 0.8 millimeter hole, it's unclear how safe it is to fly MS-22 back down to Earth with 2 cosmonauts and an astronaut on board. And this has led to several weeks of various discussions. They're dealing with a variety of different constraints. So first constraint is how quickly can they get another spacecraft up there? Well, you can fly both the Dragon crew capsule and the Soyuz capsule fully autonomously. They can get themselves to the ISS and dock, no big deal, without humans on board. It's unknown right now how fast SpaceX could get a Crew Dragon prepared. NASA has asked the question, and we're all waiting for the answer. Roscosmos has said that they can have the spacecraft that was already in preparation for MS-23 that was scheduled to launch in March, ready by or around February 19th. So the general feeling is if everything is allowed to proceed as is and there's no emergencies or anything else, that we're going to wait until the next Soyuz capsule can get up. Now, this does cause a fair amount of butterflies in the stomach.
They don't have a lifeboat.
They don't have a lifeboat. And not only that, but while we're like pretty sure that something externally hit in the exact right place to exactly hit this coolant tube, it's unsure exactly what happened, which is always something that creates a queasy feeling. Mm-hmm. But the current plan is that failing anything else, we are going to wait for MS-23, while also waiting to hear from Gwen Shipwell when SpaceX will have a capsule ready, please, soon. It's interesting times.
Yeah, we should say that a lot of the concerns around the Soyuz are around the flight computer. So there's really no indication that structurally there's anything wrong with the spacecraft.
Yes.
It'll hold air, it has life support, all of that. What they don't know is when they turn the flight computers on and they start generating heat, will that heat overwhelm the system?
And
there are go ahead.
That actually led to a really interesting thing that I read in TASS. And there's this saying that if something is denied that no one has asked, that you weren't thinking about, it's probably what actually happened. And in TASS, one of the Roscosmos officials is quoted as saying that the people saying that inside the capsule reached 50 Celsius is not true. And I hadn't actually heard that anywhere until I read that quote. It's understood that temperatures did rise to at least 40 Celsius, that everyone will admit to, prior to them shutting off the computers. They now have things equalized out at 30 degrees Celsius, which is still pretty uncomfortable. Yeah. And they can land without those computers. However, they land on land. And the problem with landing on land is if you miss your landing spot, you might end up in a forest, and they land in Kazakhstan, which means you could land in a forest with bears.
Right. Well, they've got shotguns on board to deal with that.
After several hundred days, I wouldn't want to have to fight off a bear. Right. I kind of would want to be picked up and carried away. So this is a very uncomfortable situation because they don't want to have to land without the navigation computers. They don't have a lifeboat. We are hoping that they will actually be ready by mid-February to launch MS-23 autonomously. And I misspoke. It's Gwen Shotwell, not Shipwell.
Yeah.
Gwen Shotwell, we're waiting to hear from you. You are our final hope.
Right.
It's one of those things where, it's like if you just like went rock climbing or something, and somebody told you when you got down, oh, by the way, your harness was unattached the whole time. It's like we've been 20 plus years and have never encountered a situation where it's been necessary to use the lifeboat functionality of the spacecraft in the way we're thinking about right now.
Yeah.
But now that suddenly we don't have it, it makes you sort of think again about how sure are you really that, and it would have to be like a station-wide problem. Like if there was a medical emergency or something, they could load any of the astronauts onto the SpaceX capsule and send them back down. It would have to be there's a micrometeorite in the ISS and we can't stem the leak or something like that, which is never come close to happening. But you want that protection.
Yeah, I mean, in theory, a Crew Dragon can handle 7 people.
Right.
So,
right. They were engineered for 7. They took the seats out. The life support, etc., is probably still sufficient for that.
Yeah.
But you need the right space suits.
You kind of duct tape them to the wall.
Yeah, I wonder, like, would you, in an emergency, would you prefer a Soyuz that is already 30 degrees and has no coolant, or a Crew Dragon that's only meant to carry 4 people, but it has room and probably can handle 7 people? I'd take the Crew Dragon, personally.
Yes.
Well, and you could put on an EVA suit, and EVAs are much longer than the time it would take to emergency return to Earth. So you wouldn't even need to rely on the Dragon life support. As long as you could be
secured,
held down to survive the re-entry shocks, I think you would probably be fine.
Yeah. So I wonder
these are the kind of risks that astronauts take that, like, most of the time things work fine. But then
bear,
you have to do
shock.
Yeah.
Bear.
Yeah. Bears are fine. I'll take a bear encounter over a lack of coolant or having to get stuffed into a capsule any day. But I have bears that poke around my house.
Black bears I'm fine with. Grizzlies not as fine with.
They don't have any grizzlies in Kazakhstan. They're only in North America, so don't worry about it. Black bears are like a big dog. They're just a big silly dog. You just go, "Hello, bear," and then the bear runs off into the forest. That is my experience with bears. That's Fraser's training on bears is wave to the bear and watch it scamper away.
There are grizzly bears there.
In Kazakhstan?
They're called the Kamchatka brown bear.
In Kazakhstan? Kamchatka and Kazakhstan are very far apart.
They have them not in North America. I'll stop there.
Right.
I'm Googling here, folks.
Yeah. I played Risk. I know where Kamchatka is.
Yeah, you're right. It's closer to Alaska.
To Alaska, yeah. All right. Well, we've reached the end of our show. So, Morgan, what are you working on? And where can people find out more?
Oh my gosh, I am working on nothing related to space, which you may have been able to tell from my performance tonight. We've got some cool stuff happening at Adventure Science Center here in Nashville. Definitely come check out our Recycle Rainforest exhibit, which will be here through March. You can learn about the rainforest, build your own rainforest creature, and find out why recycling is good and deforestation is bad.
Have you seen this show on Disney Plus called Lieberman is in Trouble, I think it's called? It's really good.
Lieberman?
No, it's a different. It's
Lieberman is in Trouble. No, I have not.
So good. It's so good. And one of the sort of common themes of the show is they have a Vanta Black exhibit at the local museum that the various family members attempt to go into this exhibit, and it freaks them out every time they get anywhere close to it. It's like this haunting nothingness void. Is that a real exhibit that's going around? A Vanta Black exhibit?
It's not. You can paint things with Vanta Black or some of the other ultra blacks and teach interesting things about light and how our brains process the world through light. There's lots of cool videos on YouTube of people painting rooms black and then going in, and as they walk away, it looks like they're just shrinking
Yeah.
Those kinds of things don't work so well, and they work better on cameras than they do in person. And that paint is both like pretty toxic and super, super fragile.
Right.
And so you have to airbrush it on, and it's a whole thing, but it's super, super cool.
Yeah.
And I am certainly thinking about ways to use it to talk about light. And,
yeah, but if you can do
perception.
a Vantablack exhibit like this show, it made me think of you. And the other thing that made me think of you actually is we're rewatching The Detectorists, which is one of my favorite shows. And there's an interaction. Essentially, the main characters are metal detectorists. And the stakes are very low on this show, right? Like dealing with Nighthawks, people who come in who raid archaeology digs at night to try and sell the stuff, or people being an archaeologist and trying to deal with engineers trying to build on locations. So anyway, it's a great show, but there's interactions with people who work for the British Museum, and it's quite funny because it makes you sort of think
people bring in. One day at my old job, I was walking by the front. Somebody walks up to me and hands me a box and says, "This is full of mice. Please feed it to your snake." And it's like, well, who do I call to have received a mouse delivery as I was like walking from my office to the bathroom? That's just like everyday occurrences.
Yeah, for sure. Pamela, what are you working on, and where can people find out more?
Well, I now think I'm going to be working harder at catching the mice in my house now that I know I can just send them to Morgan and he'll get them fed to a snake.
I could do this too. I've got lots of mice here, Morgan.
Feed your bears.
Anyways, we are getting ready this Friday. We are launching a new show over on CosmoQuest called Escape Velocity Space News. Essentially, we are repackaging Daily Space, except instead of working each day to record a half-hour show, we're going to put all of our effort into doing one really good show each week. And
wait, a weekly space news show?
Yeah, but different audience.
But you don't hang out.
Yeah, we don't hang out. It's just going to be different. So we're going to be starting that, recording this Friday, looking to air on Now Media Network. Check your local TV listings a week from Saturday.
Fantastic. And of course, I am all Universe Today and all the things. And I just did an interview with Dr. Adam Frank, who is at the University of Rochester. And he used to be the blogger for NPR, but is also really big into astrobiology and has a lot of great ideas. And so he's come up with this idea, which is like Pamela's perfect asteroid spacecraft maker, where you surround a rubble pile asteroid like Bennu in a bag, and then you spin up the asteroid and it turns into a torus. It turns into a donut that you can then live on the inside of the donut. So it's way easier than trying to hollow out an asteroid and spin it up. And it's a really clever idea. And we had a really good time. We talked about that and other things. And I actually just did an interview with Maura Bajah, who is a aerospace engineer who is tracking space debris and has built this really amazing application. Actually, I'm going to put a link in the in the comments so people can check this out. But it shows you the distance, how far. So you guys can see this too. It's how far away different objects in space are getting with each other, and so over the last couple of minutes. And so you can see back around 30 minutes ago. No, sorry, around 1 minute ago. Is that right? Okay. Anyway, like within the last hour, two objects came within about 500 meters of each other in space. And this just happens all the time.
Too close.
Yeah. It's just like in real time, you can just watch objects in space buzzing past each other. Anyway, so we talked all about detecting space debris, how busy is orbit right now, and what can we do to mitigate some of these problems going forward. So it was a really fun interview, and that'll be out in the next couple of days. All right. Well, thank you everyone for joining us this week on the Weekly Space Hangout. Thanks to all of the moderators. Thanks to everyone watching us both on YouTube and on Twitch. Thanks to our special guest. Thanks to my co-host. Thanks to Nancy Graziano, as always, for keeping us all organized. Pamela, you did double duty, both guest and engineer. So I'm just going to thank you twice. Thank you. Thank you. We will see you all next week. Thanks, everyone.
Bye-bye.